Good morning, everybody. Very good. Let's recap what we discussed yesterday. I hope you are able to retain the material we discussed yesterday. We started with texture. We talked about what is a texture is all about. It's inclusive of mechanical properties, rheology, microstructure, everything in between, right? That's what we started with. And then we looked at it, rheology, what is rheology all about, and then we moved on to mechanical properties. Within the mechanical properties, we talked about force deformation. Just a force deformation data will not be sufficient. Really have an objective understanding of the material. So we have to convert the force deformation to stress and strain, and that will be a very meaningful way of characterizing the material. And that will also have the, if there are two labs doing the same test for the same material, they will have a similar information with the same configuration and things like that. We also talked about what kind of sample size we want to use it, shape we want to use it, and we come to a conclusion that cylindrical sample will be better opportunity because it has only 2 dimensions. Even though sphere has a 1 dimension, but it is hard to make a spherical sample. So cylindrical sample will be easy to make compared to other sample sphere. You can also do a cubical thing, but the issue with the cubical sample is when you apply in one direction, the deformation go into the other 2 directions or 3 directions. One direction normal, the deformation, the height decreases and it will expand in the length and width direction. Then it's very difficult to analyze the more correct manner, more proper manner. So cylindrical samples are better, and that is most of the time people use it a lot of times. And then we looked at the force deformation, stress and strain curve, and there are 4 different important points you can get from that data. One is linear limit, the other one is elastic limit. Any material you do force compression test, each one have a small amount of linear limit. If you can identify that smaller amount of linear limit, the loading and unloading will be the same, meaning that every material will have a small amount of elastic component. So it could be 2% deformation, 5%, 10%. We don't know how the material will behave. So any material will have, all the material will have a small amount of linear limit, which means that they are purely elastic in that linear limit. Then we talked about elastic limit. It's also same thing, going and coming back will be the similar way. And then we talked about bio-yield point, where there could be some damage within the cellular matrix, within the structure, which we will not see that in naked eye. And then last thing is rupture. Rupture is the collapse of everything, and then from that data you can get the total energy input, strain energy density, and then we also looked at it, what's the unit of that, how much energy goes into per meter cube of the sample, joules per meter cube. And then we did small conversion, and we found out how to get the joules per meter cube. From Newton per meter square, you can get joules per meter cube just by substituting numerator and denominator with the meter. Then we went on to look at the elasticity and plasticity. Whatever is not recovered is plasticity. Whatever you can recover, that's elasticity. And we looked at 2 different ways of expressing that, either through the area under the curve or looking at only the strain level. We also found out that area under curve is more accurate than strain exposed strain of the material during the experimentation. No, please come on in. I mean, anybody can come in, anybody can go out, no issues at all. So that's what we looked at it. And then, so from that calculations, then we moved on to the tensile properties similar to compression properties. We also looked at the modulus of elasticity, elastic Young's modulus, shear modulus, bulk modulus. Those are all there for understanding, but primarily we look at only compression test, and modulus of elasticity is the main information we use it for comparing different samples. We also looked at the ductile properties and brittle properties. Brittle is one thing where immediately it breaks. Ductile means it elongates to some deformation and then it takes a little more time to break it. So when you convert that to stress and strain curve, there is a necking going on. With the brittle one, stress will be decreasing while necking is there. But in the ductile one, the stress keep increasing until it ruptures. And that's where we ended yesterday. Did I miss anything? Oh, Poisson's ratio, right, good, very good, Poisson's ratio. See, it always helps when you have only one brain compared to many brains, right? That's what I said yesterday morning also. It's not that I'm expecting everybody to learn everything, but everybody will get something out of this course. That is a good thing, right? We took a look at the Poisson ratio. So there we looked at it. When you apply a force in the normal, the deformation happening, height is decreasing and diameter is increasing. So you have both the transverse strain and lateral strain. From these two numbers, you can get Poisson ratio. Poisson ratio can vary from 0 to 0.5. Maximum is 0.5, whereas material is incompressible. You cannot compress it, no porous spaces in the material. That will have 0.5 highest Poisson ratio. 0 means only pore spaces, so immediately it will collapse. So that will be Poisson ratio of 0. Okay, anything else we missed? Young's modulus? Yeah, modulus of elasticity, Young's modulus, both are same, and we know how to calculate those kind of things. It has the same unit as stress. When you do the stress over strain, which is modulus of elasticity, you will get the same unit, Pascal, kilopascal, megapascal, right there. Anything else I missed?
Apparent one and modulus of elasticity versus.
Okay, that's good point. Because the material we are dealing with, these are all, it's not purely elastic material, which we don't want to deal with that when you are eating. So purely elastic material, we get the modulus of elasticity, but that's only case for the purely elastic material. But our food material, they are viscoelastic, so that's why we have to use term apparent modulus of elasticity, because we are assuming that our food material behave as a classical elastic material, but which is not the case. That's why we have to use apparent modulus of elasticity. Apparent means we are considering this as elastic material. That's why it's apparent. It's not actual modulus of elasticity. Okay, anything else? Okay, so we will stop there. And today my plan is talk about more the more rheological stuff. More importantly, this morning we are going to discuss about the viscosity. Rheology is all about viscoelastic nature of the material, because our food materials, they are viscoelastic. We don't have any food material which is 100% elastic, 100% viscous. So it is always viscoelastic material. All the food materials, whether it's a natural material or you are making product development, everything is only viscoelastic. So far we looked at the elastic component of it. This morning we are going to look at the viscosity of the material, because that is very important also. Once we do that, later today, after first lecture and the next two lectures, we will be looking at the viscoelastic characteristic of the material. So that is our plan today. Any questions anybody has? Okay. So now let's move on to the, okay, one more thing is, I just want to mention here, Rheology of Food Materials Introductions. I'm just following the schedule we have. So the title will be like this, but when we go inside, you will get more in-depth information. That's what we're going to do. So today's topic is, this morning topic is on viscosity of the material. What is viscosity means? How do you measure the viscosity? Is viscosity same for all the materials? How they are different? How do you classify different fluids and things like that? Again, what is rheology? Rheology is the study of deformation and flow. We know about this, and rheo means flow, current or stream. So far we looked at the solids, how they deform. Now we are going to look at the fluids, how they flow. Fluids flow, solids deform. So when you think about fluids, how many fluids are there in terms of state of matter? There is a solid, there are two fluids. One is liquid and gas. We all know that, right? So in terms of, if you look at these two pictures here, what you see here is the somebody is under the water, so liquid is going to flow, even air is also going to flow, and these are all about the, we are going to study this morning. Before we study the viscosity, principle of viscosity and other things, I just want to mention to you what are the common rheological instruments we all use for our study purposes. You can classify them. One is objective test equipment, the other one is subjective. When I say objective, what is come to your mind? Just out there, I mean, objective means what? What's that? I am not hearing you. Oh, multiple choice questions? Oh, okay. No. Objective means here, when I ask you objective, she told me that it's a multiple choice question. I didn't mean to that. I didn't mean that way. Objective and subjective means, objective is you get the quantitative information which can be reproduced using different instruments. For example, if you use the texture analyzer, texture compression testing machine, you get force and deformation. If you use force deformation data only, or force with respect to time, that will be subjective. On the other hand, if you convert that force with respect to time or deformation to stress and strain, that would be objective. So the stress and strain data will be, you will be getting it from any instrument you use it, whether you get it from your lab or somebody's lab, that will give the, supposed to give the same data, same information. That is objective instrument. The instrument you use or test you use in the instrument, and those tests are called objective test. There is no discrepancy between different instruments. There should not be. But in actual case, it may not be the case. And there will be some differences for whatever reason, because the operators are different and they may not repeat the same thing every time they do the test. So there will be some variations between the lab to lab, instrument to instrument, but the variation will not be that great, that much. It's only very small amount. So that's called objective test. Subjective test means the results you get from subjective test, they may not be reproducible from one lab to the another lab, from one instrument to the another instrument. And those tests will be instrument specific tests. And those results may be subjective based upon what instrument you use. So that's the difference between objective test and subjective test. Make sense? So when we do the actual instrument, when you talk about other instruments, then you will know little more about it. So objective test measures fundamental properties derived from stress strain which are independent of apparatus use. That's what the objective test means for our discussion. So if you look at these different instruments, you will be exposed to at least this the top portion of it. I think you'll be using an instrument called rheometer on Friday, and you will have exposure to that on Friday, and that is called the objective test. Um, for example, in this rheometer, you can use different configurations. What you see here is it's a parallel plate, meaning that there's a bottom plate, there's a top, what is that called? Probe. So you can put your sample between the bottom plate and the probe. So your sample goes to in this section, in the top section. You put the sample there, and then you lower the probe, and then you can compress it, or you can do oscillation test, things like that. You can rotate your probe. We will talk more on that this afternoon, but that is called the objective test. Parallel plate, and you can also have a concentric cylinder. Concentric cylinder, we'll talk more on this in this session. This is basically, you have a cylinder, and then you have your rotor there. So your sample to be tested is placed inside the cylinder. So you lower the probe, and then you rotate the probe. So the probe will be shearing your sample against the cylinder here. So we will be doing these type of tests. At least you will be able to monitor them on Friday when we do the concentric cylinder configuration and try to measure the viscosity of the fluids. That is a plan for Friday morning. And then cone and plate, as name implies, there's a plate in the bottom and there is a cone on top, and then your sample is in between. Sometimes it's semi-solid food, mayonnaise, ketchup, and things like that. You can put it here, and then you rotate the cone so that there is enough contact between the cone and the sample and plate. And the issue is here, the issue is slippage. Sometimes your sample may slip out of the plate here, so you may not get the quality data. But this cone and plate, you will get the quality data because there is good contact between the cone and your sample. And then there is another configuration is called mixer. So material to be tested is put it in the cylinder here, and then there is a vein attachment so that you can mix the sample and you can find the rheological properties. So these are all something about the rheometer. This is objective test. And then you also have other ways of measuring the viscosity using capillary tube, high pressure capillary, and pipe. So these are all different configuration instruments available in the service scientific community. People use it in different cases. Again, these are all primarily for the liquid materials. You can measure the viscosity of them. This is also liquid, this is also liquid, and this is for solid, this is for solid, this can be for semi-solid also. So these are all different configurations. You can use either one of them for depending upon what samples you have. The next one is subjective test. The subjective test means it measures the empirical and generally instrument dependent characterization. They are primarily empirical. They do not, the empirical correlation means they can change it. It's not like an objective test. They are purely very objective way of measuring things. Here more subjective way of measuring things. You may be familiar with the pheronograph, mixograph, and all, right? Yes? Okay. Primarily they are used for dough characterization. When you have a roti dough, things like that, so you can use the pheronograph, mixograph. When you look at the results of that, the results you get some number, but sometimes those number may not have any proper unity to it. That is why it's called subjective test. I also put texture profile analysis because in my opinion the TPA test very commonly used, it's more of subjective test because we do not get stress strain data, or we do not characterize the material based upon stress strain data. Primarily it is characterized based upon the force and time or force and deformation data, even though it has a unit. But again, we discussed about it yesterday, force deformation data may not be always correct way of analyzing it. You need to convert it into stress and strain. Why we cannot convert that in the TPA, I will explain to you tomorrow when we talk about that. Because it's TPA test is primarily, it's not a one bite, one compression only. It is a compression, decompression, compression, decompression. Because that is we are trying to mimic how we eat. Because when we eat food, we do a lot of biting, right? It's not just one bite, two bite like that. It's more than that. Number of bites. It all depends upon individual consumer, right? Because Nivedita will do 15 bites. I may do 10 bites. Primarily because I'm a hurry. I want to get it over eating. I want to get my work done. So I may not have a similar number of bites. Okay. But if you really want to be healthy, you have to do as many bites you can. Take your time to eat the food instead of hurrying things and then eating food. That's one way to control your digestive system also. Spending more time while eating, it's better than spending less time in eating and then worrying about too much about other things. Any questions so far? Okay. Okay. TPA means it's called, okay, the question is what is TPA? TPA means, as name implies, texture profile analysis. This involves, I can explain to you now for a quick conversation, but I will explain in detail when we meet tomorrow. I have more information to discuss on that one. So TPA is nothing but, yesterday we talked about this compression only, right? Loading, and also little bit we talked about unloading also. Okay, so this is one bite, biting, releasing. So this is one bite, and then there will be some particle sticking to the teeth. So that is adhesive to your teeth, and then second bite will be like that. So that's why it's called TPA, texture profile analysis. This is the important point, hardness, and then with this information you can calculate other properties: cohesiveness, springiness, resilience, chewiness, gumminess. So we will do this exercise tomorrow morning so that you will understand a lot better. And then we will sorry. I made a mistake. This afternoon, when you go to lab, you are going to measure the viscosity. Okay, rheometer, viscosity. That's what you are going to do this afternoon. On Friday morning, we will do TPA. We will have a in-class activity here tomorrow morning, and then Friday morning we will have a TPA, texture profile analysis. Okay, so you will compress some sample, you will do some double bite test and all on Friday morning. Am I right?
Sir, today we are doing compression test in texture analysis.
Okay.
We will do rheology later.
Okay. Okay, so you are going to do only one compression test, only one bite test only today.
I can demonstrate it, but explanation can be given.
Correct, yeah. Perfect. Okay, other questions? Yes.
Sir, in the previous slide, the equipment slide, you told we can use solid there. So what you measure in solid viscosity?
No, let me explain to you. Good question. I in when I discuss about this one, I mentioned that you can use solid here, solid samples here. You can also use solid samples here. Primarily because what I meant was this kind of instrument is very sophisticated instrument, and then you can take a small piece of your sample and then place between the two parallel plate. In this way, what you can do is you can characterize the surface phenomena of your solid samples. When I say solid samples, I didn't mean to say all the solid samples. For example, cheese. You can take a slice of cheese, that's solid sample. You can put it underneath here, and then you can evaluate the viscoelastic nature of the material. You won't be able to put your other solids. I mean, you can get slices of any sample and then measure the viscoelastic nature. We'll talk about that this afternoon. I will explain a little more on that this afternoon. Very good question. Other thoughts?
Sir, is there any single instrument in which both solid, liquid and semi-liquid sample can be tested?
Okay. The question is there any single instrument which can be used for solid, semi-solid, liquid food? Yes, there is one, and that is the instrument called rheometer. Rheometer? Yeah, the rheometer is different than the viscometer. Okay, I'm going to explain to you. The rheometer, you can use it, like for example, this instrument. This is not an instrument. This is the different configurations. The rheometer is the instrument which can be used for solid material, semi-solid material, and the liquid material also. So same rheometer, you can use it to measure the viscosity of the fluids. You can use it to measure the viscoelastic properties of solid, semi-solid material. The textural analyzer can be used only for solid materials. That cannot be used for other form of materials. That is why textural analyzer is only 25% cost of the rheometer. So there is a limitations in each instrument. Other questions? Okay, we looked at this one yesterday also. We will be looking at this today also and tomorrow also. So far, yesterday we talked about solid, elastic behavior nature. Now we are going to look at the viscous behavior, fluid. So within the viscous behavior, there are Newtonian fluids, non-Newtonian fluids, meaning that Newtonian fluids are time independent, meaning that no matter how long you run the experiments, they will have the same property. That's what time independent fluid, and which are called Newtonian fluid. And then non-Newtonian fluid can be time dependent and time independent. Primarily, we will be talking about the Newtonian fluid, and we will be talking about time independent non-Newtonian fluid. You will be surprised when we talk about those things, saying that, oh, there are different types of fluids we have. You probably expose that, okay, give me viscosity value, my life is good, right? I need one number, then I can live with that. It's not that easy. If you really think viscosity as a one number, you are making a big mistake, because until otherwise, if the fluid is Newtonian fluid will have only one viscosity number. No matter how long you run the experiment, how many times you run the experiment, you always get to one viscosity value if it's a Newtonian fluid. Non-Newtonian fluids, the numbers will be different depending upon how fast you measure them, for how long you are going to measure them. Make sense? So we will talk more on that down the road also. So there are Newtonian fluid, non-Newtonian fluid, which are time independent. There are some not non-Newtonian fluid, they are also time dependent, but that is above and beyond our discussion. We have a lot of materials to cover, and typically these time dependent fluids we don't experience in day-to-day life. Typically we experience only Newtonian, time independent, non-Newtonian, which is also time independent. Time dependent fluids, it's more classical examples are there, but mostly for scientific curiosity, people study those materials. Okay, what is fluid now? Let's look at what is fluid. It's a continuous amorphous substance whose molecules move freely past one another and have a tendency to take the shape of their container. For example, you have honey, you have ketchup, you have mayonnaise. They are all flowing fluids, right? So if you put them in the container, they flow. When you pour them, they will flow and they occupy the container space. That's what the fluid flow means. And then they are made of molecules. They move each other, they move past each other, they shear. That is how you measure the viscosity. That's what the viscosity is all about. How much they shear each other. That's all about the viscosity. There are two types of fluids, we looked at it. Liquid, visible type of fluid with a relatively high unit density. Vapor, relatively low unit density, right? Vapor, low density. Liquid has a high density. Thicker the fluid, more density, higher the density in general, but that may not be true all the time. You still can have a thicker fluid, their viscosity may be less than some thinner fluids. So it is not always true saying that, but in terms of day-to-day life understanding, you can think like, okay, thicker fluid will be higher viscosity, thinner fluid will be low viscosity. But that may not be true all the time. Okay, what is a viscosity? It's internal resistance to flow. Let's say you have some type of liquid, it looks like a water, but it could be any fluid for that matter. So they move past each other and the resistance to flow, and that's what the viscosity is all about. So you see a shearing going on between molecules, and that's what the viscosity. It's resistant to the internal friction of the fluid caused by the molecular attraction. What you want to measure? It's indirect measure of product itself. Important that we want to know the viscosity of fluid, primarily to understand the product itself and product consistency and quality. This kind of information also very important when you are designing pumps, piping systems and containers. High viscous fluid, you need more energy to move, right? You cannot use the same pump to pump the milk and use the same pump to pump the ice cream, right? They may go in the same line in your product in the industry, but they cannot keep changing the pump size, right? So they need to have higher pump size so that they can run both the milk and ice cream in the same line, because otherwise it will be more expensive. having separate pumps for the different fluids, that may not be feasible. If you think about that, you need to have different pipelines, different pumps. It is going to occupy more space. Space is expensive, right? The less space you have, it's better. Always it's more economical, more efficient also. And also the flow behavior is related to quality and function of the material also play a role. So now you see that importance of measuring the viscosity. Okay, we talked about molecules, shearing between the molecules. So what happened? There are two molecules, they are going to shear past each other, and this is the sheared area, and that is the what this viscosity is all about. When they flow past each other, you are going to measure the resistance to flow, and that's going to give you you are going to calculate the viscosity based upon that information. Yesterday in the elastic discussion, we talked about regular stress and strain. Here we are talking about shear stress and shear strain, because molecules are shearing each other. So you are calculating the shear stress and also the shear strain or shear rate. Shear strain or shear rate, both are same here. Shear stress is force over area, so it's a shear stress, and shear strain is a deformed by time, deformation over time. Question? Which one? Okay, the graph is basically what it says is the molecules are going to shear each other. So there is a force applied. And there is a deformation because of that. In a plane, there is a force applied. Because of the force applied, there is a deformation in the plane. So that's what the D is all about, deformation. And this is force. And the force over area, what area the contact is there. So force over area is a shear stress. And also how much in terms of time, what is the deformation, and that gives the shear rate or shear strain. Okay, let me correct myself. This T is not time, this is the thickness or height. So that's what you get. So D is the deformation and this is the thickness or height, and from there you get the shear strain. So once you know the shear stress and shear rate or shear strain, you can calculate the ratio of the shear stress over shear rate. That is the shear modulus. This is shear stress, and this is shear strain. Viscosity is nothing but shear stress over shear rate. Not shear strain, it's a shear rate. How much is shearing per second, that dictates the viscosity. So viscosity is slope of the shear stress and the shear rate. The one other way to visualize this is, let's say you have this cylinder here. Well, it's not a cylinder, it's a cup. You have fluid here, and if you want to measure the viscosity of the fluid, you can put a spoon here and shear them, right? So when you shear them, depending upon the viscosity of the fluid, you will experience resistance. If the highly viscous fluid, when you are shearing them, it will be harder to shear. If it is low viscosity fluid, when you shear them, easy to shear. So that is the concept. That's how you have to understand the viscosity. So let's say you have two sheets and they are shearing each other, and when you have the different velocities going in bottom and top, when they are shearing, you are offering the force. There's a force going in, and this is the area, force over area is shear stress, and the shear rate is nothing but the velocity gradient. This is stationary, this is moving, so the velocity gradient, this higher velocity, zero velocity, always in the bottom, zero velocity. So velocity will be increasing from bottom to top. Top will have a higher velocity, bottom will have a no velocity. Because this is stationary, this is a moving layer. So there will be layers from top to bottom when you look at the continuous material there. So they move each other like that. And that's what you get in terms of the velocity gradient over the shear strain rate, how fast you move them or how slow move them. And that's where the time variable comes in. Let's identify the state of matter in this image. Let's say you are boiling the water. Liquid is in the bottom, and then you get vapor. So this is also flowing, and even water also flowing there inside, right? That's a fluid flow. And that's the way you can understand the viscosity also. Okay, now let's talk about the different fluids now, types of fluids. I discussed before also there are Newtonian fluids and there are non-Newtonian fluids. So if you measure the shear stress with respect to shear rate, so this is shear stress and this is shear rate. Typically unit is 1 over second. Shear stress is Pascal. So this is Pascal, this is 1 over second. How fast you shear them or how slow you shear them. So if the shear stress over shear rate is linear, this is linear, those fluids are called Newtonian. Because if you take a slope of this line, which is viscosity, you will get the same value. So viscosity will not be changing for the Newtonian fluid. Everybody with me? So these are all Newtonian fluid. If the shear stresses keep changing with respect to shear rate, those are called non-Newtonian fluids. And there are different there are different classification within the non-Newtonian fluids. If the shear stress is changing exponentially for a given shear rate, that's called shear thinning. Shear thinning means if you take a slope of this line, the slope here will be higher and it will be slowly decreasing. Slope is the viscosity, right? Shear stress over shear rate is viscosity, similar to elasticity, modulus of elasticity, stress over strain. Here same thing, shear stress over shear rate, that's called viscosity. So shear thinning means initially it will be harder to shear. At a higher, if you keep shearing faster, easy to shear. That's why it's called shear thinning fluid. Shear thickening, on the other hand, initially it's easy to shear, but as you keep increasing the shear rate, it will be harder to shear, and that's called shear thickening. And for example, shear thinning fluids are orange juice concentrate, mayonnaise, and then shear thickening fluid also called their example is cornstarch and water suspension. Sometimes the shear thinning fluid, also called pseudoplastic, and shear thickening is also called dilatant. Those are all different terminologies. So do not worry too much about it, Just a different way of describing things or different terminologies. There are fluid, they will need to have some yield point, jump starting it. There is a starting trouble, you need to start them. So they will have a yield stress. So as soon as you shear them, it will be very harder to shear. So they will experience that. So that's called yield stress. And then it will be a Newtonian behavior, similar to here. And those fluids are called Pingham plastic. Example is toothpaste is one of the Pingham plastic. So in fact, if you have a toothpaste tube with you, you have to really put force in the beginning to start the flow, and that's called the yield stress. And then once you start doing that, then it keep coming out, and that's one way to visualize how that toothpaste behaves. Yes, ma'am.
For pseudoplastic fluids, it's shear thinning. So that means the shear rate decreases with time. The shear rate will decrease with time. That means the molecular attraction will decrease with time. And how does this happen actually?
Okay, the question is the shear thinning fluids. The stress will be decreasing with the time. Stress will be decreasing with the time. I'm trying to think how to explain that. Stress will be decreasing with the time. Okay, let me rephrase my thing here. So shear thinning fluid, it will be difficult to shear in the beginning. So that's why you have a higher shear stress. Once you start shearing them, keep shearing them faster and faster, it will be easy to shear. So as you increase the shear rate, which is how fast you shear them, it will be easy to shear. So viscosity will be decreasing as you increase your shear rate.
For pseudoplastic fluids, this thing is happening.
Correct.
And for dilatant fluids, the opposite thing is happening.
Correct.
So why is this happening? The opposite thing.
Why the material is behaving like that? Yeah. That is inherent nature of the material itself. That's how the material are formed during the processing. That's given. That's the nature of the material. That's what we are trying to study here, right? Right? I mean, if that's a material you need to work in your plant, then you need to have a proper equipment to move the fluid. That's what we are talking about it. This is inherent, this is the nature of the material itself, and that's what we are trying to characterize them. I'm not sure why it became shear thinning or shear thickening. You know what I'm saying? There's a pure nature of the material itself like that. In fact, even the water starch suspension, if you just take only water, that's purely Newtonian, right? Even if you have a cornstarch more than 80-90%, you cannot even move them. So there is a clear differentiation there. So your cornstarch is 60%, water is 40%, then they behave as shear thickening. And that is a molecular rearrangement and the chemistry of the material. As an engineer, I do not worry too much about chemistry. I mean, when I say I do not worry too much means things go above my head. So I don't. again I am a left brain person, right? I don't analyze too much. If something comes up, that's what it is. That's not a clear, that's not a great answer for you, ma'am. But if you want to go further, you need to study lot more chemistry material to really understand what is happening. I think that is the out of scope of this information, what we are trying to share. But very good question though. Okay, how do we model this data? Because we can collect a lot of data. If there is a way we can get couple of numbers so that we can compare the samples, that would be great, right? Otherwise, if you are doing product development and then you are getting a lot of curves like that, how you compare the different graphs? See, like for example, if I take the shear thinning fluid, this is like this, this is like this, this is like this, this is like this. How do I compare the different shear thinning fluids? If there is a way we can model that and then get a couple of important information from the whole curve, that will be easier, right? And that's what the Herschel-Bulkley model tells you. The main model equation is shear stress is equal to initial shear stress plus shear rate, K times shear rate over N. So if you take a log of that, so this goes to left hand side. So if you rearrange this equation, minus tau 0 is equal to K times N. Right? Same equation. I write it like this. I can write. Everybody follow that? And this is to the power N. So if you take a log of this, so log of this plus is equal to log K plus N log shear rate. So the exponential thingamajigger became the linear here. So once you rearrange that equation, when you plot this data, shear stress over shear rate, shear stress over shear rate, then you can get K and the N value, and you can compare K and N value for different fluids. We are trying to simplify here so that easy to understand. So this is the tau is shear stress, yield stress is tau 0, strain rate or shear rate is gamma to the dot. N is called flow behavior index and K is called consistency coefficient. Okay, so I regraphed this one here, shear stress over shear rate, shear stress is Pascal, shear rate is 1 over second, Newtonian fluid is here, dilatant or shear thinning is here, shear thinning is here, this is shear thinning, this is shear thickening. This is Pingham plastic. I also added Pingham pseudoplastic. Pingham plastic is similar to this one with the yield stress. Pingham pseudoplastic is similar to pseudoplastic except the addition of yield stress. So if we go back to that model equation, which is the tau is equal to tau 0 plus K T N. So these fluids, they don't have the yield stress, so this is 0 for these 3 fluids, right? And the Newtonian, for Newtonian fluid, N is 0, N is 1, N is 1 for Newtonian fluid, so we get shear stress equal to K times shear rate, so K is the viscosity. So if you take a slope of this line, that is eta or mu viscosity, which is tau over shear rate. Make sense? And then for the dilatant fluid, N will be greater than 1 and yield stress is 0, right? There is no yield stress for this dilatant, but N will be greater than 1. If N is less than 1, no yield stress, that's called shear thinning, pseudoplastic. The Pinkham pseudoplastic, N is 1, but yield stress is there, so tau 0 is greater than 0. So that's how you interpret the whole graph. So in fact, what it means is, if you go back to this graph here, well, not only this graph, if you go back to this graph here and then model this with this one, your values will be different, K and N will be different, and you can get the differentiate between the different fluids based upon this K and N values. Fluid is flowing, you all know that, right? It's a laminar and turbulent flow. Laminar means it's a very streamlined flow, there is no turbulence. That's why it's called laminar flow. How do we differentiate between laminar and turbulent flow? Reynolds number. Thank you. Reynolds number, if it is less than 2100, it is laminar. If it is more than 2100, turbulent. Or to make it much more clear, if it is more than 10,000, definitely it's turbulent. If it is in between 2100 and 10,000, transition, meaning that it's both turbulent and laminar is there, experiencing it. And this will be, information is useful when you are designing the pumps and things like that, in addition to your viscosity data. What's a unit for Reynolds number? No unit, correct? Things cancel out because Reynolds number is rho d u by mu. Rho is density, d is the diameter of the pipe, u is velocity, and the mu is viscosity. So if you put the units, everything cancels. That's why it is number. This is density, velocity, viscosity, and this is diameter. Some subjects are a little harder to understand, some of them are easy to understand. So I am trying my best to cover the materials here because it's a little more complex in terms of understanding the viscosity compared to elasticity, because it needs a lot more thinking to really understand the viscosity. When you really get into that, if you just measure it, you get a number, life is good, right? You don't worry about anything. Okay, let's look at the different fluids here. The unit is primarily important for me, so unit is nothing but Pascal times second. because if you go back to that diagram here, shear stress is Pascal, shear rate is 1/2, so viscosity is mu is viscosity Pascal times 1/2, you get Pascal times second. I think Umesh won't like this one. I should not be writing it here. So centipoise is a very old unit, okay? But these days we use it in Pascal times. That is the proper SI units. Pascal times is units for viscosity. So you can see different fluids here. Gas is very low viscosity, liquid is some numbers, and then viscosity of paste and things like that, which is much higher number. Shear stress over shear rate gives you the viscosity. Lot of times we use apparent viscosity. Why? Because we are considering the non-Newtonian fluids as a Newtonian fluid in a given shear rate. That's why it's called apparent viscosity. Only Newtonian fluids has one viscosity number. Non-Newtonian fluids, viscosities keep changing. That's why we call it apparent viscosity. Okay, now let's come to how to measure viscosity. There are a lot of instruments available there, different varieties, you name it, you can get viscosity, viscometer. Okay, it all depends upon how much you want to evaluate your samples, how much information you want to collect from your sample, and that limits your instrument. Post-wick viscometer, if you want to measure the viscosity of ketchup, that is a very simple instrument. You don't need the rheometer to measure the viscosity of ketchup. You can use this instrument to measure the viscosity, and then Oswald viscometer also there. It's basically, it gives you the one number. These things gives you one number, if that's what you want. Sometimes product development, that's all they care about it. One number, give me a number, life is good. If the number is less, I know it's low viscosity. Number is higher viscosity, I don't care about characterization. But if you are a scientist, you want to make sure that you characterize your fluid first, make sure that it's a Newtonian fluid or non-Newtonian. Accordingly, you classify it. And very important that you do that if you are a scientist. If you are a product development person, no worries, you just measure one viscosity, life is good. That's what yesterday department head was telling, right? They want to find the crunchiness of the chips, so they don't have time to do instrument measurement. So they ask the people to do it, sensory analysis, much easier, right? When I say much easier, as a person tasting different chips, much easier, they can do faster. They are trained people, they can do faster. If you take the chips and put it in the texture analyzer, you collect the data, you come back, analyze it, and then you have a statistical analysis package, you evaluate the statistical significance. By the time consumer is out, right? Your customer is out. You don't have time to do that, right? So this is very quick, dirty method of doing it, but you get good results, and then you can move on with your product development. There is another instrument called falling ball viscometer. Basically, you have a liquid which has a density. You drop the ball, depending upon how fast this ball moves, that dictates the viscosity of your liquid. From that, you can calculate the viscosity. That will let you know that what is the viscosity of your fluid, and then make sure that is following these standards. I come up with some example problem. I don't have time to do this now, so we will skip the example problems. And then this is a Brookfield viscometer. A very simple instrument. Again, you cannot characterize using this instrument. You can only measure one viscosity number. I'm going to show you two more viscometers. Capillary tube viscometer. Basically what it is, you have a flow going through the pipe, and then you measure the pressure difference, pressure here, pressure here, pressure difference delta P. Higher viscosity fluid will have higher delta P. So from that equation you can calculate the viscosity. Delta P is the main thing here. It's a function of pressure difference, radius of the pipe, length of the tube, and volumetric flow rate. So if you cancel all the units, you get Pascal times second. I also have the example problem here. You can use these individual data to calculate the viscosity of the sample. It's here, shown here. That's for the capillary tube viscometer. Next one is rotational viscometer, which we will be doing that on Friday. Basically, there are two cylinders. This is a cup and this is a bob. So you rotate the bob and put the sample inside the cup. And this is the equation you use to calculate the viscosity. It's a measure of torque. High viscous means higher torque value. Low viscous means low torque value. Unit cancels, you get the Pascal times second. And we are running out of time. So I like to stop the discussion here, and I'll take any questions you might have now. We will discuss more on Friday when we go to lab session, where I will explain to you. We will do some testing of the samples, and I will clearly characterize at least 3 different fluids, Newtonian and non-Newtonian fluids. Questions? Last minute questions? Yes, ma'am.
So when we are characterizing the rheological behavior of fluids, sometimes we keep constant stress and we measure strain. Sometimes we keep constant strain and measure the stress. So it is like, is it specific for some products? For this product we should keep constant strain, on this product we should keep constant stress, like that, or it's just our way of.
Okay. The question here on the floor is, I think she's just jumping into the next chapter. We are going to discuss about it this afternoon, which is good. It's a good transition. So when we come back after lunch, we'll talk about that, constant stress and constant strain, why we are doing one way or other way. Just wait for another few hours. We'll come back and talk about that. Thank you. Good transition. You all have a great rest of the morning and also lunch. We'll come back at 12:45 sharp, so that we can continue our discussion with the viscoelasticity. So far we talked about the elasticity, viscous. Now we are going to look at the viscoelasticity of the material. And that's the plan for this afternoon. 12:45 viscoelasticity, and then 4 o'clock we are going to talk about the dynamic rheology in terms of constant stress and constant strain, things like that. Okay? Thank you all. See you later.